Please welcome Mark Ricklick from Embry Riddle.
All right, thank you everybody for having me. So I'm going to talk about two topics that I'm very excited about or interested in, gas turbines and heat transfer. And so just to kind of kick things off, I've got two images at the top here, a gas turbine for aviation propulsion or jet engine turbofan, and a gas turbine for power generation, so large turboshaft engine. And the problem we'll look at today, or area of interest for my research, kind of interested in both of those. And so the bottom two images are kind of examples of what happens if we do not do a good job at cooling gas turbines. On the left here, we have a nozzle guide vane, first stage nozzle guide vane. You can see the front's been burned through. And the second here is a later stage rotor, and you can see the tip and the trailing edge region are kind of melted away. And so we'll talk about some of the work we've been doing to contribute to designers trying to prevent these effects. So just a brief introduction of myself. Mark Ricklick, as was mentioned. I did my PhD in mechanical engineering at University of Central Florida down the street, also working in the area of gas turbine heat transfer. After that, I spent a couple more years at UCF as a postdoc, still working in gas turbine heat transfer, various cooling techniques, doing some projects with NASA and Siemens Energy, which is right across the street from them. After that, I spent a couple years at a company called CD Adapco. They develop a simulation software, so it's helping customers carry out simulations like modeling flow and heat transfer in the automotive industry, space, aerospace, as well as like agriculture industry. And then I've been at Embry Riddle since January 2014. So we'll talk a little bit about motivation. I'll hopefully convince you that gas turbines are useful. There's still a need to do research with them. We'll talk about gas turbine cooling needs, why bother studying heat transfer in gas turbines. Talk a little bit about gas turbine operation, how do gas turbines work, what are gas turbines, so we're on the same page. Introduce you to heat transfer, kind of a branch of thermodynamics, very, very upper level. I promise only a couple equations. We'll get into how gas turbines are actually cooled, so real examples of gas turbine cooling, and then some of the research we're doing at Embry Riddle and kind of my conjectures on where I think the future will take us in terms of both gas turbines and gas turbine cooling. So first of all, why bother looking at gas turbines? So there's kind of generally, I'm making a lot of statements. I'm sure there's exemptions to everything I say. But we kind of have three main sectors where gas turbines are used. Aviation for propulsion, power generation. So for example, the power plant you see when you drive down I-4 over the St. John's, if you look to the west, there's a power plant there that uses gas turbines, natural gas-fired gas turbines. And then there's a lot of uses in industrial applications, such as oil and gas for pumping, say, natural gas over long distances, or say on oil platforms for providing power, mechanical energy at these locations. And so the plot to the left here kind of shows a breakdown of the market space, the global market space. You can see this large chunk, pretty much half of it, is made up of power generation. The other second largest chunk is industrial applications, and then that last sliver there, still a significant segment of the market, but that's made up by jet engines that you see on every airplane you use. And then the plot to the right here, again stolen from some research groups off the internet, shows kind of the growth in terms of the U.S. market size over the years. The takeaway is that all three markets are generally growing, so there's still need for research and work in these areas. If we kind of focus on each of those segments individually for a second, so first looking at power generation, where's my pointer? So the plot over here to the right is taken from the Energy Information Agency, from kind of a branch of the Department of Energy, their annual energy outlook from this year. And what it's showing is the breakdown in electricity generation from various types of fuel. So you can see natural gas that's predominantly used for gas turbines, natural gas-fired gas turbines, and of course coal, renewables, and nuclear. Again, the takeaway is even though with renewables kind of gaining a larger and larger penetration into the electricity generating market, natural gas is still one of our largest producers of electricity. Okay, so there's still a need there. How do we produce how do we produce electricity from a gas turbine? They're typically natural gas fired, so we can pump in natural gas, and the shaft output spins a generator, essentially. So you think like your home generator that we used the past couple hurricane seasons to power our houses. Same idea, but way, way bigger. They kind of come in two forms: a simple cycle, where I just basically have a gas turbine, a jet engine spinning a shaft, spinning a generator, and what's called a combined cycle, where I use that hot exhaust gas to power a steam plant. And those are actually the ones you see off I-4 passing over the St. John's. Those combined cycle configurations, very impactful. Their fuel efficiency can exceed 60%. Some of the latest configurations are getting up to like 62% fuel efficiency. That may seem low, but that's good for what's called a heat engine. And so in terms of kind of market players, General Electric, Siemens, Mitsubishi Heavy Industries, Kawasaki Heavy Industries are kind of some of the big names in this market. They produce engines that produce, we're talking imperial or English units, on the order of 800 horsepower up to 1 million horsepower. So think your car produces what? Maybe 100 horsepower to maybe 500, 600 if you have a fast car. The total electricity generation in 2010 was approximately equivalent to powering 420 million homes just through gas turbines and combined cycle gas turbines. So big impact. Some examples: this is a Siemens called an H-frame, or one of their variants of an H-frame, one of their larger engines. To give you an idea of the dimensions, I think that is, I'll show you another slide with people on it, but it's, no, I forgot my notes. About 35 feet long, okay? So around 35, big. Here's a GE, kind of similar scale. This is still in the assembly plant, so you see a platform around it, but you can see the people working on it, right? Large scale engines producing, tens to hundreds, thousands of horsepower. And these big circles here where the combustors would stick in, so again, large scale combustors where we dump in fuel, produce heat eventually. Another image, this is another GE H-frame configuration. What I wanted to point out here, this is in a combined cycle configuration. So the gas turbine is around here. The hot exhaust is being dumped out into this big, it's basically like a big radiator. We pass that hot exhaust across water and tubes, turn that water into steam, and the steam goes across the steam turbine. Right? So we're using just wasted heat that normally would have just been exhausted to the atmosphere. Upstream of that is the generator, which would be producing electrical energy. And there's even small variations of these power generation configurations. So this is an example from Kawasaki Heavy Industries, and it basically fits in the back of a truck, and you can deliver this portable power on demand to various locations. There are solutions in this kind of power range that are diesel or even traditional liquid-fueled configurations. But my focus today is trying to convince you that gas turbines are important. So how about aviation? Nearly all aircraft are powered by gas turbines, all except the smaller aircraft configurations. In terms of commercial aircraft, there's approximately 24,000 aircraft in flight, projected to go up to 63,000 commercial aircraft in the next 20 years. If you look at this plot to the right here, this is another plot by EIA, the Energy Information Agency. And this is in terms of passenger mile kind of projections into the future. And we see that air travel, the key is air travel is increasing dramatically as compared to, say, bus and passenger rail travel. So again, what powers these aircraft? Gas turbines. And we're seeing more and more people demand air travel. How do we provide propulsion with the jet engine as compared to producing power? In this case, we either have that hot exhaust leaving the engine, comes out at high speed, will push the aircraft forward, or we use some of that shaft power to spin a propeller or spin a fan. Okay, thinking in super simple terms right now. These are most typically liquid fuels, so like Jet A, as a fuel type, kind of like a kerosene or diesel fuel, very similar to diesel. They can get efficiencies by themselves above 40%. Okay, so still very good fuel efficiencies. Some of the market players, again, GE has a aviation branch, Pratt Whitney, Rolls-Royce, CFM, and there's a bunch of others as well. Power ranges, in some of the kind of main commercially available engines range from maybe 600 to over 134,000 horsepower. Yep.
For comparison, what's the thermodynamic efficiency of an 8-cylinder pickup truck?
30% if you're lucky. Okay, usually they're down, especially with all the stop and go that you do, more in like the teens, high teens. So yeah, low, a lot to be desired. And we have some advantages. Aircraft engine, you're flying at pretty much one speed. There's some variations off that during takeoff and descent and climb, but the majority of your flight, you're not stop and go in traffic, and that really has a bad impact on efficiency. Okay, some of these newer engines, automobile engines that are taking advantage of like hybrid drivetrains, they can push towards above 30%, but most generally, yeah, we're down 15 to 30. Okay. So we'll look at a couple examples. Before that, the plot here, this is from another kind of market forecasting company, Platinum Forecast, and this is showing the number of gas turbines in the aviation sector already produced between 2000 and 2018. A couple things I'll point out here. In aviation, they come in a few configurations. So turbofan, kind of what I'm showing here is a cartoon. So in this case, that's what we're used to seeing on the commercial aircraft we fly. We have a big fan swallowing huge amounts of air, and then kind of a smaller hot core flow flowing out the back. Turboprop applications, we'll see those on smaller, lower speed aircraft. Turbojet applications, we don't typically see very often anymore. They have better suitability for higher speed applications, but even the military are starting to use very small bypass or low bypass turbofans. Okay. But the takeaway from this plot on the right here is out of all the, can't really see my pointer on the top line there, there's kind of a climbing rate of production in terms of turbofans, okay? But they're all relatively steady, not a decline in any of them. Some examples, turbojets. The GE J85 is probably one of the most popular turbojets, heavily used by the military. And then turbojets kind of find their applications as well in the RC market, so kind of toys. And so the two I'm showing to the left there are examples of JetCat. The top is the P20. It produces on the order of like 5 pounds of thrust. So it'd be a little toy remote control airplane. Guess how much it costs for a toy? $100, like $2,000 or $3,000. So expensive, right? One of the drawbacks to gas turbines. And the bottom here, Jetman, he's flying with 4 of JetCat's P200. So they produce about 50 pounds of thrust each, like a $5,000 or $6,000 per motor. And then looking at an example of a turbofan, kind of one of the next generation turbofans, GE Gen X. To give you an idea of the dimensions, I didn't write that down. But producing on the order of 75,000 pounds of thrust, so large amount of thrust to be used on the 787 and some of the variants of the 747. Okay, and we've seen all these turbofans, maybe 8 feet in diameter at the inlet here. Okay, so relatively large. There's other applications as well that I won't get into as much, but industrial, I mentioned that, like platform, oil platform, power or shaft power output. Marine propulsion, a lot of the large military ships will use, and this is an example of a military ship using a gas turbine to drive a generator, that generator providing electrical power for whatever electric motors they use to propel the ship. And then there's also been kind of an ebb and flow of interest in gas turbines for automotive applications. There's a big push maybe in the early to mid 80s. They have drawbacks in automotive applications that we'll talk about. One of the only examples nowadays is this is a kind of a shot through the back window of Jaguar's CX-75, and it's a hybrid, but it uses turbines instead of a reciprocating engine to give a range extension, basically recharge the batteries. Okay, so one of the only examples. It looks kind of cool to me. So hopefully it convinced you that we use gas turbines. They're not old technology. So next, try and convince you that we need to cool gas turbines. So without going too deep into kind of the thermodynamic operating principles, one of the main drivers for gas turbines' fuel efficiency is the turbine inlet temperature, the combustion gas temperature. So I'm kind of circling the hot section of both of these engines. Again, aviation engine on the left, power generation engine on the right. And basically to increase my efficiency, one way to do that is to increase the temperature of the gas going out of the combustor into the hot section. Okay. Another way is to increase the pressure ratios, but I'm not worried about that right now. So state-of-the-art engines right now have combustor outlet or turbine entrance temperatures, so the maximum temperature in the engine, on the order of 3,000 Fahrenheit. The state-of-the-art materials that we use, so these very expensive, they're single crystal super alloys, very, very expensive materials, can only withstand up to 1800 degrees F. So there's a big difference there, right? Almost 1500 degree F temperature difference. How do I do that? I can only do that by cooling the components. So the only way I can do that is by cooling these hot section components. What we'll show later, though, is that doesn't come for free. So kind of a recurring theme today will be, there's usually no free lunch. Sometimes we'll find it. So next, I'd like to spend a little bit of time talking about the operation of a gas turbine, kind of get us all on the same page. What is a gas turbine? Very basically, it's an air-breathing heat engine. So air-breathing, that means I'm using air as my working fluid. I'm bringing air in. I add heat to it, and by allowing that heat to flow through my engine, I'm extracting some of that energy that I've added by combusting my air. Your automotive engine, same thing. It's also an air-breathing heat engine. Okay. Different though, our gas turbines operate on what's called the Brayton cycle. Doesn't matter. And you can think of it as a series of rotating kind of airfoil-shaped blades on a shaft, and we throw a combustor in the middle of them. So it's kind of the cartoons that are shown down here. I have a bunch of blades upstream and some blades downstream, and there's a combustor in the middle of them. Okay? These airfoil-shaped blades, airfoil meaning they do, and I'll show some examples later, but they do kind of look like an aircraft wing. They're turned a lot more. But they allow us to manipulate the airstream, so increase the pressure of the airflow coming in. They also allow us to either convert shaft power to airflow or convert airflow to shaft power, and we're going to do both of that in various parts of the engine. It kind of operates on the concept of suck, bang, blow. I suck air in, bang, combustion, blow, I blow it back through the turbine section. Okay, and we'll talk about why. A big difference between gas turbines and, say, reciprocating engines that we're familiar with, piston-style engines, they're continuous flowing. So it's not an intermittent, suck, bang, blow. It's continuously flowing through the engine. That kind of gives us some operational advantages sometimes. But from a heat transfer standpoint, that's the challenge, is everything's kind of continuously occurring. So there's another kind of schematic to get an idea. The upper image here is a configuration where we have a turbojet configuration. The bottom is a turbo shaft, so it could be a turboprop or a power generation engine. And so again, very simply, it's I have some blades in the compressor section, some blades in the turbine section, a combustor in the middle, air flows through, the compressor draws the air in, it heats up, it blows, spins the turbine. And then for the turbojet application, that gas then is just let to exhaust back to ambient, comes out fast. That's what pushes us forward, like a balloon that you fill up and let go, that's producing a thrust. For the turbo shaft application, I have some additional blades on a shaft downstream. The air rushing by will spin those blades, spins a shaft. I can do whatever I want with that. So more to make it in terms of some engineering quantities. So the upper schematic here is my turbojet. So I have my inlet. I slow the flow down a little bit. I go through my compressor where I bring up the temperature. So this blue line here, I bring up the pressure. The blue line here is pressure. The red line is temperature. So as I compress the air, I'm doing work to it. So the temperature is going to rise, even though I would like it not to, but it's going to rise anyway. The temperature coming out of the compressors can be on the order of 500, 600 degrees, depending on what pressure ratio we operate at. I go through the burner or the combustor, I dump in fuel, I bring that temperature way up to my maximum temperature, and then I let that high temperature, high pressure gas rush out through a turbine, and then out the back of the engine. Okay, so the pressure and temperature kind of continuously drop from there on. So let's look at each of these components just a little bit more. So first of all, the compressor. The goal of the compressor, bring up the pressure. Again, these airfoil shapes, so I got a cartoon and then a real image on the right-hand side. This real image on the right-hand side is only showing the rotors. Okay, so in a real engine, it's made up of rotors, so these rotating blades are really doing all my work, and stators, stationary blades, they're really just there to kind of guide the flow back. And so, and they're stages of these, so rotor, stator, over and over again. And so this rotation of these blades kind of draws in air, and because of the shape of the blades and the shape of the flow passages, I can increase the pressure of the air as it moves through. And so modern engines, modern aviation engines are pushing 50 times compression ratio. So the air comes in and is increased 50 times what it was at the inlet. So that means that sea level conditions, that's about 700 psi, all by moving across all these kind of very thin airfoil shapes. Think of it like a series of fans, right? So I have one fan, and I put another, and I have a duct behind them all. But what do I need for my fan? I need power input. In this case, I need shaft power input. So this shaft, something needs to provide me power to spin this shaft. And so that'll come from the turbine later. So air comes off that. we have one of the benefits of gas turbines is we move a large amount of air, so we can generate a lot of power for a small volume. That's too much air, though, to maintain a stable flame, so we bleed off just a little bit of that air into the combustor or into the primary zone of the combustor. We add fuel, whether it's natural gas or propane or JP8 or whatever the fuel is, liquid fuel, gaseous fuel. We mix it, we ignite it, we have this continuous flame going, and then we bleed in the rest of the air. That's called the dilution zone in this area. What that's doing is it's bringing the air, this high pressure air that exited the compressor, it's bringing it up to some elevated temperature that we have a target for. Like I mentioned, that can be up to 3,000 F in some modern engines. Probably military engines, higher than that, we're not sure. That's occurring at a relatively constant pressure. So we're ideally not losing any pressure. The left face here is the compressor exit. The right face here is the turbine entrance. And this is kind of the combustor cutaway there. And so again, the air kind of flows in, bleeds in these holes. This would be my fuel injector. It ignites, and then the rest of the air kind of bleeds in and mixes with this flame and bring that temperature way up. Okay, and obviously we want to control that temperature. We'd like it to be nice and uniform temperature, ideally. So that hot gas, high pressure, high temperature gas comes out, and then we go through our turbine stages. Now the turbine is also a series of airfoil-shaped blades, rotor stator passages over and over again. And so, again, I'm showing rotors here with the stators missing. If you notice these blades compared to the compressor blades very skinny, and there's a lot of rows of compressors. In the compressor, I'm pushing the flow from a low pressure to a high pressure. Flows don't want to do that. That's called an adverse pressure gradient. And so we have to be very gentle. And so they're very thin so as not to disrupt the flow, and we do it just a little bit at a time per stage. In the turbine, this gas wants to go from the high pressure it's at back down to ambient atmospheric pressure. And so because that's a favorable pressure gradient, I can be a lot more aggressive in my blade designs. And so you see these are much thicker airfoils, and look at the turning angle on them. They're doing a huge amount of work per row. Okay, so as this high pressure, high temperature gas rushes past these rotor blades, it imparts a torque and starts to rotate them. Torque times an RPM gives me power. That power is transmitted back up to the compressor. So the turbine and the compressor are on the same shaft. Okay, so once everything's up and operating, the power coming from the turbine spinning the compressor. Okay, so like the compressor was a series of fans, the turbine's a series of pinwheels, right? One feeding into the other. So how do we generate from this compressor, combustor, turbine configuration, these different engine configurations? What I just described is at the top left here, what we call a gas generator. Okay, so that compressor, combustor, turbine, that turbine just produces enough power to spin the compressor, and it's leaving me with this high pressure, high temperature gas. What I do with that differentiates what engine configuration I make. If I just exhaust it back to atmosphere through a nozzle, I get a turbojet. If I add another turbine stage and use that turbine stage to, say, spin a big fan, I get a turbo fan. Or I can add some additional turbine stages and use that additional power extraction that I've done from the flow to spin a shaft to either spin a propeller or a generator. So, but the key is they're all the same in terms of the gas generator, and the area I'm interested in is really the highest. This is where we see the highest temperatures, highest pressures, the highest thermal loads against these super alloys that we're putting in there. So advantages: very few moving parts, very high reliability. The waste heat, we don't need a radiator on a gas turbine. That it's all just going out in the exhaust. Relatively high efficiency, very high power densities. Some of the drawbacks to gas turbines: they're expensive, like I mentioned. They don't idle very well, so your car will idle at a few hundred RPM, maybe just under 1,000 RPM. Gas turbines will idle in like the thousands of RPM, tens of thousands depending on the size. So burning a lot of fuel just sitting there not doing anything. They don't change power very quickly. They take time to start up. I talked about the compressor challenges. The compressor requires a lot of power input, and the turbine has to overcome that. And so that makes some challenges in terms of design. And then what I'm interested in is this hot section temperature capabilities. Okay, and we talked about generally the efficiency, the fuel efficiency, and the power density, how much power I get per weight or per volume, increases with my pressure ratio, my compressor pressure ratio, and TET, my turbine entrance temperature, or that hot temperature that I'm generating. And so to prove that, this is kind of a historical plot from the 50s when gas turbines were really commercially introduced. They were uncooled versus kind of projections into kind of near future. the improvements in materials, so the metal capabilities over the years, there's a slope, but it's not very drastic. So materials have gotten better over the years, but not as much as what cooling has done for the allowable turbine entrance temperature. So cooling, gas turbine cooling has really been the primary driver for our ability to increase the gas turbine entrance temperatures. So what is heat transfer? This is where I have a couple equations, but I promise we won't go too deep into them. So heat transfer is related to the first law of thermodynamics. It's basically a mode to transfer energy, and it's the resulting transfer of energy when two bodies are communicating that are at different temperatures. So I have a hot block and a cold block. I let them communicate somehow. There's energy being transferred from one to the other. That's what we call heat transfer. So this equation here, this is the first law of thermodynamics in steady state for an open system. I'll show you just the couple things we care about. So this first term here is the energy coming into this kind of volume we're looking at. It has temperature and it has a velocity with it. So it's carrying some energy with it. It's leaving at potentially some different temperature, some other velocity. If I don't add any energy to the flow or take any energy out of the flow, then the temperature and the velocity will be the same. What came in, what went out, everything balances. Otherwise, I have ways to transfer energy into or out of the system either by heat transfer. So, my little candle cartoon here, I add heat to the system. In our case, it's going to be combustion. Or I can have work transfer. So I spin a shaft. In our case, we'll be spinning a turbine wheel. Okay, those changes will affect whether it's the velocity or the temperature. Okay, so I'm changing the energy of the system. And what we're focused on in terms of heat transfer is this Q. So there's three primary modes of heat transfer: conduction, convection, radiation. Conduction is basically heat transfer through a solid, you can think of it. It's due to molecular diffusion. Molecules are bouncing around. We increase the temperature. They move around more. They bump into each other. They lose energy, and it kind of propagates along. Okay? Convection is when I have, say, a hot body or a hot block, and I blow air across. I have a moving fluid field, and that aids in kind of the removal of heat. So that's where that advection term comes from. Radiation we're not going to look at, but that's basically electromagnetic transmission of heat. So if we look at this, we have a campfire. It's almost wintertime. If I stick a hot rod into the fire, okay, it's being exposed to the heat, and my hand is colder, or my glove is colder, and so there's conduction along that rod due to molecular diffusion. If I put my hands above the fire, there's that draft of hot air coming up, so that heat's being carried to my hand by conduction, and to the side, it's primarily due to radiation, right? So the heat you feel from the sun is radiation. We're going to mainly talk about conduction and convection. So conduction, like I said, it's typically think about it when we're talking about the thermal energy transferring between or through a solid. So if we take this kind of generic block over here to the right, let's just imagine one side is held at some high temperature, hot temperature, and the right-hand side is held at some colder temperature. So these three different solid blocks, they're acting like a resistance to the heat that's trying to go from the high temperature to the low temperature. Heat always wants to go from a high to a low temperature. Okay, so you can think of heat transfer like a voltage and current. So the conduction, the heat trying to travel through this solid is being resisted due to the thickness of the material and what's called the thermal conductivity. Okay, so very good thermal conductors are like copper. Poor thermal conductors are like the insulators, that we have in our attic and so on. Okay, and so I can increase or I can reduce the amount of heat that's coming across here if I hold these two temperatures the same by either increasing the thickness or reducing the thermal conductivity of each of those. Right? Or if maybe the rate of heat passing through, so the Q was constant, my electrical current's constant, I can increase the temperature difference between these by, again, trying to increase the resistance. Right? So the temperatures and voltage potential are very similar to each other. So our goal when we're talking about conduction, at least in this case, is we want to try and avoid exceeding some allowable metal temperature. And we'll point out shortly why conduction will be important. Convection, a little bit simpler to think of. So again, I have this hot egg there. I have a fan. I'm trying to cool it down. And so there's essentially temperature. If I look at this bottom plot to the right here and look at this, this is kind of a schematic of our temperature distribution of the air going from the surface of the egg out to the room temperature. And so the temperature will kind of slowly decay from the surface temperature of the egg back to the room temperature. And that's what's called a thermal boundary layer. And so we can reduce the temperature difference between the air and the surface of this egg by basically increasing what we call this heat transfer coefficient. And so that's kind of my research group is focused on is trying to control this heat transfer coefficient. And so from a convection standpoint, in the gas turbine, we have two goals. Our goal is to control the heat transfer rates. In some cases, we want low heat transfer, so we want nice smooth flow. We don't want to disrupt that thermal boundary layer over there. In other cases, we want high heat transfer, and so we want to try and promote mixing and beat the thermal boundary layer up, right? Try and get the cold fluid from the room. Can't see my pointer, but get the cold fluid from the room down towards the surface of the egg to promote the mixing. So it's great. I just come up with a geometry that improves heat transfer. But again, there's typically no free lunch. There's a relationship between the convection, the rate of heat transfer due to convection, and the friction or the resistance to me pushing the flow over that surface. And it's approximated by what's called Reynolds analogy, and it basically says these two quantities are similar to each other. So if you think I have a pipe and I'm trying to remove heat from it, if I want to push more flow, or I make some fancy geometry features inside there to remove more heat, usually that's going to result in requiring a larger amount of power to push the flow through there. Okay, so and we'll see where that power is actually coming from. So the plot here is taken from Ronald Bunker. He used to be kind of the best heat transfer guy from GE. He retired, that's why he's not anymore. And so this is showing the friction, or kind of that resistance to pushing the flow, versus the heat transfer due to convection on the y-axis. And the dotted line is Reynolds analogy. And most of the common cooling geometries that we see in gas turbines actually do worse than Reynolds analogy. There's a few that kind of lean on the better side, but really this is where we want to be. We want to try and beat Reynolds analogy. We want to remove a lot of heat, but require very little power to push the flow through that cooling channel. So there's no free lunch usually, and there are some kind of fancy ways we can try and beat that. So now we're starting to get into actually cooling gas turbines. And so let's first kind of visualize the thermal environment for a blade. So these cooled blades, and I'll show some examples later, but they're hollow essentially, and we'll pass coolant through them. And so if I have this generic turbine blade right after the combustor, I have hot gas coming, the leading edge of my blade is going to have the highest thermal loads. Okay, so that's going to be the hardest to keep from melting. This bottom surface here is called a pressure surface. That's going to have typically my second highest. The trailing edge will be the third, and what's called the suction side will typically have the lowest thermal loads. And that by thermal load, I mean the hot gas trying to heat up the metal itself. Okay. So if we look, just another kind of cartoon of a generic turbine blade, this kind of a isometric view. I have my coolant passing through these individual channels, the hot gas moving on the outside. And what I want to point out here is kind of where this conduction problem comes in. So this bottom layer here is my airfoil material, the super alloy, nickel alloy that I'm using. This middle one we don't care about. And this outer layer is called the TBC, or the thermal barrier coating. And so that's commonly added now to engines. I'll show some pictures shortly. It's essentially a ceramic coating that's trying to act like a huge resistor to the heat trying to come into the blade from the hot gas to drop the temperature across it. So very low thermal conductivity, a large temperature drop across it, so it's kind of protecting the metal blade underneath there. So kind of schematically, if we take, let's assume this is just some generic slice of a turbine blade. On the bottom here, I have my internal cooling of my blade. My outside up on the top, I have my hot gas moving by. I tried to hack together an old image I had, so ignore the line there. And so if we look at I mentioned heat transfer being very similar to electrical current flow. So resistors due to all these transfers of heat. And so on the outside here, I do like very low heat transfer due to convection. I'm trying to maximize the resistance in that. I don't want the hot gas pushing heat into my metal. I have my thermal barrier coating. I want very high resistance here so that I get a large temperature drop across it. So I want low thermal conductivity and maybe a thick thermal barrier coating. My metal, so this is going to be my maximum metal temperature here on the upper surface. My metal, we'll say in a second, but we'd like that to be a low resistance. And then my cooling, I would also like a very low resistance, very high heat transfer coefficient, because I want the temperature of the metal here to be very close to my coolant metal temperature. And the higher my heat transfer coefficient is, the lower my thermal resistance, and the closer those two will come to each other. And then, of course, I'd like this as thin as possible so that the temperature drop between here and here is minimized. right? But this is where my failure point is. And this is how I'm trying to protect everything, is by cooling from the backside. So what do these blades look like? Then the next couple slides, I'll just give some examples of cooled turbine blades. So the upper image here is IGT's industrial gas turbine, so like a power generation gas turbine. First stage nozzle, so this guy takes the brunt of the thermal load. He's right after the combustor. His job is to turn the flow into this first stage rotor down here. It looks like Swiss cheese, right? It's covered in holes. And so these are called film cooling holes, and I haven't even talked about that, and we won't except for these images. But basically I'm bleeding coolant through this blade. It does its job on the inside of doing internal convection, and then it comes out on the surface here for kind of one last shot at protecting the blade. It tries to make like a blanket of, I can show you from here a little better, but it comes out of these small holes, and you try and get a blanket of coolant on the surface to one more step in protecting the blade from the high temperature gas. It's kind of white colored, and as well as this first stage rotor, that's that thermal barrier coating. So these all have thermal barrier coatings on them. The second stage rotor down here, notice it's uncoated. Okay, so the temperature drops as I move through all these rotating components because I'm extracting energy from the flow. And so by the time I get here, there's no need for this coating. Obviously, coating is one more step in the manufacturing process. It's expensive. You can imagine all these holes I either have to go plug or drill through afterwards. So if we don't have to coat it, we don't need to. You also notice these last blades are less heavily cooled than is compared to that first stage rotor, or first stage guide vane. Another image, not the kind of blurry, but this kind of shows a 3D view of some generic turbine blade, sort of like an X-ray. The takeaway is there's all these crazy cooling channels inside there. These are maybe a little more descriptive. So again, generic blades from the literature. Coolant's coming in through this one from the base, comes up through here, and I have these kind of cooling passages on the inside where it zigzags back and forth. There we go. So it kind of comes up and down, works its way. I have impingement cooling on the leading edge because that's where my max thermal loads are. It kind of zigzags back and forth through some pin fins at the trailing edge. I'm pointing both those out on purpose. And then it's ejected out the trailing edge. I have some rib turbulators in the middle there. And then of course some film cooling on the surface. And then another example to the right. Okay, so these blades, even though they look relatively simple from the exterior, minus the Swiss cheese look to them, we have all these crazy cooling channels inside. And here you can see the number of passages. I keep mentioning generic because engine manufacturers are very secretive on state-of-the-art cooling configurations. It's kind of one of their strongest IPs. And then two more. So the takeaway is tons of different cooling configurations used in the literature. But we've seen a bunch of times, hopefully, impingement has been used a few times, and pin fins or cylinder arrays in the trailing edge. I'll point those out because those are two areas that some of my students are working on. So it's great. We just pump a bunch of air through these blades, cool it, no big deal, right? Where does that air come from? So we get that air. Basically, we're stealing it. Generally, we're stealing it from the compressor. All aviation engines are air-cooled from the compressor. There are some power generation engines that will use steam, like external steam. So basically, we do this work to compress this air, right? It took a power input into the compressor to bring that air up to pressure. Then I bleed off a little bit of it, skip the combustor, so I'm not adding that energy from the fuel into the air. And I use it to cool my turbine, but I'm not really getting any energy back out of it. So it's a parasitic loss. And so Ron Bunker, I mentioned earlier, kind of had a good quote regarding that. Some modern engines will use up to 20 to 30% of that, the air that comes in through the inlet of my engine, 20 to 30% of that could be used for cooling. And so in order to justify that, you have to be able to prove that basically your efficiency gains outweigh the penalties. So I need to be able to push that turbine entrance temperature, my combustor outlet temperature, high enough that me stealing air from the compressor, that penalty associated with that is beneficial. And so what are some of the challenges? Those parasitic losses I just talked about. So there's a lot of work in trying to maintain heat transfer rates while reducing our coolant usage. Okay. Otherwise, or the pumping power, so the pressure drop associated with it. Durability, so clogging, especially in aviation, flying through dusty environments, can clog, for example, some of these film cooling holes. They need to be able to withstand that. And then predictability, that's a big one, is we may do a good job at cooling, but how do we know how well of a job we do? And we don't really know to a very high level of accuracy, and so how do we compensate for that? We add extra coolant. So we're having an efficiency penalty there just because we don't know how good of a job or how poor of a job we're doing. And so kind of research needs, first of all, we can always push the turbine inlet temperature higher. I mentioned we're on the order of 1,500, I'm going to SI for a second, but we're on the order of 1,500 degrees centigrade for now. The maximum temperature we can get out of a fuel, a hydrocarbon fuel, is on the order of 2,500 degrees C. So we have almost 1,000 degrees C room to increase temperature. What's limiting us is our cooling capabilities and our material capabilities. I talked about predictions. Uniformity is another research challenge. It's one thing to cool this blade. It's another thing if I have very cold spots and hot spots right next to it. I have thermal stresses that kind of negates the cooling I've done. And the big one, and really what I'm focused on mostly, is reducing those parasitic losses. And so with the last few minutes, we'll talk about what we, and by we, I mean my students, and I'm just watching them, but what we're doing on it over at Embry Riddle. It's a big summary, but we're basically doing a lot of different things. Some of the more interesting things, we're doing what's called biomimicry. So we're trying to kind of take advice from nature and try to implement those into heat transfer designs. Optimization with kind of the goal of 3D printing these geometries. And then we're also, and I've got some better pictures, but we're also looking at what's called unsteady impingement and then a bunch of other things. That cartoon we use, I'll show a picture of it again in a second, but that's temperature sensitive paint. We basically have a paint that kind of glows in the black, not a black light, but a UV light. And how much it glows is proportional to the temperature. So I have some fancy camera that picks up those temperatures. So I talked about pin fin cooling in the trailing edge. We've done quite a bit of work in pin fin cooling, mainly with the goal of, so these two images here and this image at the top here are CFD, they're simulations we've run. And so we have some simulations and we have an experiment. And if you've never done CFD or simulations for flow and heat transfer before, kind of the word of advice is garbage in, garbage out. It's very hard to know how to set up your model so you get accurate answers. And so we kind of have an experiment and simulations going on at the same time and trying to tune these simulations so that they match our experiment. Because at the end of the day, simulation should be cheaper. I don't have to build up hardware. I can let the computer do the math while I'm at home. But it's very easy to get unrealistic answers. So for example, these two images are of the velocity kind of through the center of this pin fin array. You can see at the top here. Just by checking two different boxes basically in the simulation. And they look totally different, they perform totally differently. So kind of guiding designers on what to choose. But I want to lead that into the biomimicry stuff. So the flow over cylinders, if you can imagine this pin fin array is, like I said, it kind of goes in the trailing edge section of the blade. It's basically a bunch of cylinders sandwiched between two walls. And so flow around a cylinder is unsteady. You kind of have these wakes shedding off of it back and forth. And so this is a velocity or Mach number contour kind of in the middle of that channel. Right? So this channel over here, kind of you took a slice halfway up it, or this channel here, and it's kind of halfway up it. And so you have this flow bouncing back and forth. These pin fin arrays do a great job of removing heat in the trailing edge, but this unsteadiness is kind of problematic, as well as a pressure drop associated with it. And those two kind of are tied to each other. So we started looking in the literature, what are ways around this, and we came across some work that basically is based on the harbor seal whisker. So if you can kind of see this image here, the harbor seal whisker is not cylindrical. It has undulations. Here's another image of it. So kind of protrusions and divots along it. And the reason for that is those cylinders shed vortices, it's called, but they'll bounce back and forth. So if you've ever taken like a rod and push it through the water, it'll kind of bounce back and forth. Well, the seal whiskers don't want that because they use the seals don't want their whiskers doing that because they use their whiskers to track prey in murky water. And so they've evolved to have these kind of undulations on them that basically breaks up that vortex shedding and eliminates those fluttering. So people have started to look at these to reduce the pressure losses or the friction on various devices exposed to the flow. So this is some work that was done at NASA Glenn. And these are kind of turbine airfoils, and they're kind of trying to stretch one of these seal whiskers into what looks like a turbine airfoil. And they showed promising results. The pressure drop across that turbine airfoil or the friction losses were improved. And so we're like, hey, let's do this with heat transfer. And so we did. We kind of adapted some geometries to our kind of pin fin array. So here's our baseline, two baselines, some normal circular cylinders, some elliptical cylinders, and then kind of our 3 versions of biopins. Kind of first glance, not that big a difference between them, right? And so here's one of the ones we printed, 3D printing, and you can see some images of them. Again, they kind of bounce in and out on the front and on the sides. Don't look too big a difference. This is, the red is high heat transfer, the blue is low heat transfer. But if we kind of summarize those results, I'd like to operate in this 3rd quadrant here. That's the 2nd quadrant. That's essentially beating Reynolds analogy. Okay, and so what we see is we just kind of are barely, this guy here, the diamond is compared to the triangle there. The triangles are circular cylinder. I'm getting about the same amount of heat transfer, but just a little bit less pressure drop. So we're continuing to look at this to hopefully get in this you can't see that, but in this region over here, at least in this region here. Okay, but we're kind of sort of getting there. The next one, and I'll kind of jump ahead, is, promise I'm almost done, is unsteady impingement. So impingement, very heavily used in the leading edge of the gas turbine blades where the thermal loads are the highest. One of the drawbacks to impingement is it does a great job of removing heat, but at very concentrated locations. And so what we thought is, hey, let's try and get these to sweep back and forth. And there's others that are looking at this as well, but we're trying to do it passively and kind of in an easy to manufacture approach. And so the idea is if I can get my jet to kind of come over this way and come back that way, I can end up with maybe a heat transfer contour that looks like this over to the right. Again, red being high heat transfer, blue being low heat transfer. Okay. And what do I mean by impingement, sorry, is basically I have cold air up in this plenum above it, or this chamber. I force it through these kind of small holes, and it comes down high speed and hits this hot wall at the bottom. Okay, so I get jets of air, kind of like spraying a hose against the ground. I get jets of cold air hitting the surface. And so what have we gotten so far? So these are all simulation results, so you have to take them with a grain of salt. But we basically put a cylinder upstream. So here you can see that cylinder upstream of our jet. The jet is the dotted circle to the right. And here's our cylinder, and flow is coming across. I already mentioned flow separates unsteadily across the cylinder. So in this case, we're trying to take advantage of that. And you can see it is, at least in our simulations, it's pushing this jet side to side. If you look at the heat transfer rates, it's kind of smeared it out, and it's starting to do what we want it to do. So next step is to do this experimentally and see if the CFD is right or wrong, or the simulations are right or wrong. We also, and I want to include this one, this will be my last slide, because one, it makes kind of a cool animation at the bottom, and 2, this was done by a group of undergraduates a couple years ago. But basically we used a commercially available optimizer. So this tool runs simulations and kind of vary the geometry, but you have to tell it how to vary the geometry, so it's kind of the hardest part. But it'll vary the geometry seeking towards targets. And so we wanted to reduce the pressure drop, reduce the pumping power to push the air across it, and maximize the rate of heat transfer. And so we ended up with 3. The red block up here is our kind of baseline configuration, what we started with. And these 3 kind of highlighted boxes are the 3 that we said were the best. So you can see these 2 really did a lot better job. This is heat transfer on the bottom, better is to the right, and pressure drop better is down on the vertical axis. And so we printed them, even though they're pretty simple geometries, we could have machined them. But we printed them, tested them experimentally. These are simulation results from them. But we're able to prove that experimentally that the simulation was right. And so where does the future hold? In terms of heat transfer itself, 3D printing is slowly starting to come online. GE and others are using 3D printing in production. From a heat transfer standpoint, that means I can do pretty much any crazy geometry now. Those seal whiskers I can mimic in an engine. So it kind of gives me advanced cooling. There's also becoming more and more advanced are shape memory alloys. So materials that change shape based on their temperature. They're starting to develop, I'm not a materials guy, but the materials people are starting to develop materials that can withstand these high temperatures and still kind of tune them to different geometries. In terms of gas turbines, I showed earlier that alternative power or green energy is kind of making a bigger and bigger penetration into our electricity generating market. Even then, the sun doesn't always shine, the wind doesn't always blow. We need some kind of base load, and gas turbines really serve as an excellent source for that. A lot of power plants have small peaking plants. They're small engines that you can bring up. I mentioned they start up slow, but they, compared to other, like a large steam or a coal plant or a nuclear plant, they come up much faster. In terms of aviation and propulsion, a lot of companies are pushing towards electric aviation right now. How many of you think you're going to fly in electric commercial planes anytime soon? Nope, probably not. Batteries are heavy, still are heavy. They're going to be heavy for a long time. In terms of long haul flights, like the normal commercial flights we're used to, gas turbines are still going to be used for a long time. Maybe in these short, Uber Air type, hopping from here down the street, maybe we'll start to see batteries take over. But even once they eventually do, batteries and electric motors generate heat, and there's a cooling challenge there too. That's it. Sorry, I ran over a little bit of time. Any questions? Okay. Yes, ma'am.
Who's funding your work?
So I have an industry partner right now that I can't disclose, and that's the majority of it. The school funds some of my PhD students. Mm-hmm. Unless you have some money, I'll gladly do research. Yes, sir. Yes, ma'am.
What type of coolants did you use on the blades? You kept saying that you used coolants on the inside.
Oh, okay. It's always air. So it's always air that comes in the front of the engine. It goes through the compressor a little bit, and then you bleed it off. So you imagine literally there's a pipe. It's not that simple looking, but there's literally ducting that kind of bleeds some of that air off and sends it through these fancy passages through the blades. So it's all air. There's a few, I think Mitsubishi uses in their power generation engines, they'll use steam that's kind of generated off outside the engine through their combustors. You think steam is a coolant, steam's hot, but it's cooler than the 1,000 degrees C that we're trying to get to. Yes?
Does the shape of the blades when they turn affect how much air is being pushed out?
Yeah, so that whole design process, going the wrong way. So there's a couple things that come into the blade shape designs. You have so this is kind of the axis of the machine or the axial direction. You have a mass flow you need. You start off, and I skipped over an image on purpose, but nope, this way. You start off designing these purely from thermodynamics. I'm not gonna find it. There. So what's called a TS diagram, so pure just thermodynamics type analysis. That'll tell me how much mass, how much air I need to push through the engine. And the shape of these blades govern partially that, the mass flow that I generate through it, and then how much they turn the flow is how much power in or out I extract per row of blades. So all that, the heat transfer guys wish they could have control over that, but they don't. The aero guy, usually the design of a turbine's broken up. You have a structures guy, a aero guy, and a thermal guy. And so the thermal guy is kind of the last to get some say into the design of it. Any other questions? Yes.
You said that's air being injected in there? Or like
Yeah,
coming out?
air. Like it literally, you could think your jet engine, right, for propulsion, for flight. Weight is our we don't want any weight. So I can't carry coolant with me, coolant being Freon or water or anything because it's heavy. So I bring air in the front of my engine, and I do work, compress it, then I bleed off a little bit of it. So I have a pipe, basically, and connecting to the hot section of the engine.
You think it'd be better to maybe thin the walls and then add some Freon?
So I have to carry that Freon, though, with me. So it's heavy, and it's a lot, right? We burn a lot of jet fuel during a normal flight, so there's not much room left for anything else. There is, some of the future designs are trying to get these walls thinner. That's a structural limitation because these blades are spinning, thousands of RPM, and your aero engines, 10 to 40,000 RPM. The tangential load, like the pull on them, is like 2 tons per blade. So each of those blades has to withstand 2 tons. So your car hanging off of every one of them. So it's a lot of force they're withstanding. They're trying to push them thinner and thinner, but it's a challenge. Yes, sir.
So turbines that we've kind of seen that have been kind of big and getting larger, but is there like sort of research into say mini turbines? Is there energy effects on less on a smaller scale?
Yeah, so maybe 10 to 15 years ago, there was a big push for micro turbines. There still sort of is. It kind of comes and goes. There's some challenges with small scale turbines. So gas turbines have high efficiencies when they're big, As they get smaller and smaller, ideally they'd get better and better, but the problem is I have these rotating parts and then I have a stationary part above it. So manufacturing-wise, I have to have a gap between them, okay? And so manufacturing-wise, as I shrink things down, that gap becomes more and more significant. And so it becomes harder.
So do you think it's more of an aspect of, say, no one's really trying to fix that problem?
People have tried. They are still trying. There's small groups, but the interest in it is decayed. There's MIT had a lot of research on very micro scale, like button-sized turbines that were produced like on silicon wafers. They work and they'll run off like hydrogen and things like that, very light fuels. But besides the losses associated with it, you also have a high temperature and a low temperature right next to each other, and heat's kind of transferring across it. There is work towards it. There's another area that I didn't touch on, but the Department of Energy is dumping a lot of money into it, the DoD as well. It's called supercritical Brayton cycle, so supercritical CO2 Brayton cycle. And so CO2, carbon dioxide, becomes supercritical at around 1,000 psi. And the supercritical fluid is kind of acts like water or liquid and a gas at the same time. So it's got kind of the best of both worlds. You can generate a 1 megawatt. So that's one of these big turbines. Maybe not as big as the big ones I was showing, but one of these relatively large scale turbines on something that would fit small in this room with the supercritical cycle. So there's a lot of people pushing money. There's working examples of it now. That'll probably be the next big thing. Mm-hmm. Yes, sir.
Have you made like maybe skeletonizing the blades, bending in the walls and then increasing the skeleton?
Yeah, so there are design, Ron Bunker and a few of the other kind of big names in gas turbines have suggested that the next generation of blades will, I'm trying to find a good picture, well basically this core would be kind of the load-bearing part, so it'd be solid, and then you have just a thin wall on the outside that's cooled. There's some other designs out there that, like I started off saying, there's exceptions to everything I've said, but there's other designs that instead of having this disc or this hub at the bottom, you, like you said, skeletonize and put all the load bearing on the outer surface of it. So you end up with a smaller cross-section engine. There's a few people who have attempted it, and there's a few discussed in the literature. They're expensive, so it's hard for anybody to really penetrate the market. But yeah, there's options there. There's nothing to say it won't work.
Thank you very much.
Thank you, guys.